When we talk about removing microplastics from water, the most important factor is not where they come from, but how small they are. Some are visible under a microscope. Others are smaller than a red blood cell. The smallest approach, the size of large molecules. At this scale, filtration is no longer just a mechanical process. It becomes a question of physics, chemistry, and material science, because in water treatment, size determines everything. Microplastics are typically defined as particles smaller than 5 millimeters, but for environmental engineering, that definition is far too broad. In drinking water systems, we deal with large microplastics easily captured by conventional filtration. Small microplastics, capable of passing through sand filters. Nanoplastics, small enough to behave like dissolved substances. As particle size decreases, surface area increases dramatically. This changes how particles interact with membranes, filters, and even biological systems, and it makes removal significantly more complex. Conventional drinking water treatment relies heavily on granular media filtration. These systems are highly effective for turbidity and suspended solids, but their pore spaces are measured in tens to hundreds of micrometers. Many microplastics are smaller than that. This means that while treatment plants remove a large fraction of particles, they cannot guarantee complete removal, especially for the smallest size ranges. Filtration efficiency is not just about having a filter, it is about matching pore size to particle size. Membrane technologies introduced a new level of control. Ultrafiltration membranes can remove most nanofiltration targets, even smaller particles. Reverse osmosis creates a near-complete physical barrier, but this performance comes at a cost: higher energy demand, membrane fouling, and concentrate waste management. This is the fundamental engineering trade-off. The smaller the particle you want to remove, the more complex and energy-intensive the system becomes. Size is not the only factor. Microplastics come in different shapes: fibers from textiles, irregular fragments from degraded materials, spherical industrial particles. Fibers, in particular, can pass through filters even when their length is larger than the pore size, because their diameter is much smaller. Density also plays a role. Some plastics float, others sink. Some remain suspended in the flow. This makes removal behavior far more complex than simple sieving. At very small scales, filtration is no longer only mechanical. Electrostatic forces begin to dominate. Charged membrane surfaces can attract or repel particles. Activated carbon can absorb microplastics through surface interactions. This introduces a hybrid removal mechanism: part physical barrier, part chemical interaction. And it opens the door for advanced material design in future filtration systems. Removing the smallest microplastics at the municipal scale is technically possible, but not always economically practical. This is why point-of-use treatment is becoming increasingly important. Compact reverse osmosis and advanced nanofiltration units installed at the tap can provide a final barrier. Instead of upgrading entire cities, protection is delivered exactly where water is consumed. This is a shift from centralized control to distributed precision treatment. The next generation of filtration is not only about smaller pores, it is about smarter materials. Graphene-based membranes, biomimetic channels, nano-engineered surfaces. These technologies aim to reject microplastics, allow water molecules to pass freely, and operate with lower energy demand. This represents a transition from passive filtration to selective separation, a change in water treatment philosophy. In the fight against microplastics, size defines the challenge, and engineering defines the solution.